Hi class, welcome to our next video in chapter 3. Today we're going to talk about complex zeros and the fundamental theorem of algebra. So the fundamental theorem of algebra has to do with polynomials, okay? So polynomials are a large part of what we study, okay, in algebra. So the fundamental theorem has to do with polynomials. So the fundamental theorem of algebra. So every polynomial of this form, right? So p of x, a sub n, x to the n, decreasing in power until you get to your constant term, where it is a linear equation or larger, right? So the degree is 1 or more. Your lead coefficient cannot be 0, okay? And each of your coefficients are complex numbers. Okay, so they don't have to be complex numbers. Remember, complex numbers make up the real numbers and the complex numbers. So this works for the reals, but it also works for the complex values as well. So you can basically have any kind of coefficient. You can have pi, you can have pi times I, you can have 3 plus pi I as a coefficient if you want. You can have square root of 3. You can have any coefficient, any polynomial, right? Any polynomial, any linear function, anything of this form at all, okay? It will have at least one zero. Here we call it lambda, and that 0 has to be a complex value. So again, remember, complex values take up all numbers. So it could be a real, and the complex part could be 0. That's still a part of the complex number system, okay? So again, recall that every real number is part of the complex number 0, right? The imaginary part is 0 for a real number, okay? So again, basically what this is saying is that every polynomial has at least one 0, and that 0 is a complex value, okay? And your coefficients for that polynomial can be complex, real, imaginary, regardless, right? And that 0 will be real, complex, imaginary, okay? So basically what this means is that every polynomial can be factored into linear factors. Again, a linear factor is a binomial of degree 1, so something like x plus 3, or even something like x plus 2 minus 3i, right? So x plus a, or minus a complex value, because this is over the field of complex numbers, right? So this leads us to the complete factorization theorem, right? So the fundamental theorem of algebra and the complete factorization theorem go really well together. So again, if p of x is a polynomial of degree 1 or more, so linear or higher, then there exists an a value, a lambda 1, a lambda 2, so forth up to lambda n, right? So up to the degree of our polynomial that are complex values. A here cannot be 0, okay, such that you can factor your polynomial into a, right? Again, that's why it can't be 0, times x minus one of your zeros, x minus the other 0, all the way up to all of its zeros. So what this means, okay, is that a polynomial of degree n, a polynomial of degree n will have n factors, okay? So the degree tells you how many zeros there are, right? So far, this hasn't always been true. So far, we might have a 5th degree polynomial, and then we only have 4 zeros, right? Or 3 zeros. And that's because we've only been finding the rational zeros, right? So whole numbers or fractions. We haven't talked about radicals. We haven't talked about complex. So there are, if we take those into consideration, the complex zeros that are possible as well, every polynomial has the same number of zeros as its degree, okay? So, zeros theorem. If our polynomial is an nth degree polynomial where it's degree 1 or higher, so again, as long as we're having a linear function or quadratic or cubic or anything higher than a linear included, it has exactly n zeros over the field of complex numbers. So again, the complex factorization theorem and the zeros theorem is basically saying the same thing. The only difference is that this is talking about the zeros and this is talking about the ability to factor a polynomial over the field of complex values. Okay, so these mean the same thing, but they're kind of like two different parts of the same thing, right? Here we're saying we can factor it. here we're saying, well, if we can factor it this way, then that means that each of these things then are going to be zeros, right? So this also includes multiplicities, right? So if we have a repeated root, I don't know, let's say a root occurs 3 times, that takes up 3 of the values of my n here, okay? So if I had if I had a 5th degree polynomial and I had 5 of the same 0, well, that's 5 zeros, right? Just because they're not different doesn't mean that there's not 5 zeros. It's a repeated root at that point, okay? So that you have to keep that in mind here, that it keeps that the multiplicity into consideration, right? The conjugate zeros theorem. So this is important because it goes along with these complex values. So remember, complex values always come in conjugates, right? Values are the same, there's just a difference in the sign in the middle in front of the imaginary part. So again, if you have a degree 1 or higher polynomial and each of your coefficients are real values, so not complex values but real values in this case, then any complex zeros you have will come in conjugate pairs. What that means is that if a plus bi is a 0 for your polynomial, then so is a minus bi, okay, because it's a complex conjugate. So for this to be true, your coefficients have to be real values, okay? We're not considering that over the complex numbers like this one, where if we have complex values in our coefficient, it could be that a plus bi is a 0, but a minus bi is not, and that's why you're seeing complex values as coefficients, right? So if all of your coefficients are real, pi, root over 3, 2, 1/2, any complex 0 will come as a pair, as a conjugate pair. Okay. So now let's talk about the radical zeros theorem, right? So if your polynomial is degree 1 or larger, same as before, and each of your coefficients are rational numbers, okay? So this does not include complex values or imaginary, but any rational, right? So this also does not include any square roots, like square root of 3. Square root of 4 counts because it's 2, right? But no irrationals and no complex or imaginary numbers. So only whole numbers or fractions as your coefficients. Then any radical zeros will come in conjugate pairs. Okay, so again, if you have something like square root 3 as a coefficient, this doesn't work. That doesn't mean that if one radical is a 0, that so is its conjugate, right? It has to be either whole numbers or fractions as your coefficients. If that's true and you come across a radical 0, its conjugate will also be a 0 for your polynomial. Okay, so what that means is if you have a plus b square root c as a 0 for your polynomial, then so is a minus b square root c. So again, that's only if your coefficients are rational, right? If any ai, right, any of your conjugates, any of your coefficients is a radical, then it's possible that the radical 0 does not have its conjugate as a 0. So again, remember, most radicals are what your irrational numbers look like. So unless it's like something that can be simplified down into a rational thing, this is probably true, right? So again, you have something like square root 2, square root 3, square root 5 as a coefficient. You're going to have a radical value as a 0, but its pair is probably not 0. Okay, so let's go ahead and do an example. So we went over 4 very important theorems, right? The fundamental theorem of algebra, which brought us to the complete factorization theorem, which brought us to the zeros theorem. The conjugate zeros is very important because we're dealing with complex values at this point. And so on the flip side of that, the radical zeros theorem is very important as well, right? So we preface this with these 5 theorems. These 5 theorems, very important. Make sure you're familiar with those and how they work. And let's go ahead and do some examples, okay? So basically what this is allowing us to do is very similar to what we did before, which is either build a polynomial if we're given some zeros and we have some restrictions on the coefficients, right? So if I give you one of the zeros as a radical and I say all of the zeros are going to be rational, then you know that that radical 0 has its conjugate pair in there, right? If I give you a complex 0, just 1, and I say, hey, I need this polynomial and all of its coefficients are going to be real numbers, then you know that you need to use the complex conjugate of that, right? Same for when we factor, right? We're going to use the same thing that we normally do, the synthetic division, right, as well as the rational zeros theorem, and we're going to whittle down our polynomial as much as we can until we're left with hopefully a quadratic, and then we can use the quadratic formula and then find any radical zeros or rationals or complex zeros that might show up, right? So here, same thing as normal, right? We're not going to go about this any different. We're going to find all of the possible zeros, all the possible rational zeros. So we're going to find the factors of 1. Here, this coefficient is 1. So it's really just plus or minus 1, right? So either positive 1 is a 0 or negative 1 is a 0. And based on the way it works, we're just going to try it several times. So again, I always start with x equals 1. It's the easiest. So we set up our polynomial. Notice here that the cube term is missing. So we keep that placeholder. Remember, this is very, very straightforward, right? 1 plus 0 is 1. 1 times 1 is 1. 0 plus 1 is 1. And then 1, negative 3, negative 3, negative 7, negative 7. And it doesn't even matter. I know this is not 0, so I don't even have to actually add it together, but it's pretty easy. It's negative 8. I know x equals 1 is not one of my zeros. It's not a 0. That means that x minus 1 is not a factor, okay? So I don't have to try this one anymore. I can just go ahead and move forward and try the next one, x equals negative 1, okay? Set it up, same thing, 1 plus 0 is 1. Multiply, I get negative 1. Add, I get negative 1. Multiply, I get positive 1. Add, I get minus 3. Multiply, I get positive 3. Add, I get negative 1. Multiply is positive 1. Add, and it's 0. So x equals negative 1 is a 0. Okay. So we know that that works. And this is our remaining polynomial, constant x, x squared, x cubed term, right? So I'm going to just go ahead and start with negative 1 again. Start it all over. So I get 1. Multiply is negative 1, add is negative 2, multiply is positive 2, add is negative 3, multiply is positive 1, and works out again. So x equals negative 1 is so far a root of multiplicity 2. So that means x plus 1 is a factor twice. Okay. This is my remaining polynomial. I can try this again and use negative 1 one more time, or I can see that this is constant x, x squared. Maybe I just write it and try to factor it. If it doesn't factor, use the quadratic formula, right? So again, this is what we have so far. Very, very obvious when we write this in polynomial form that this does not work, right? This does not factor over the reals, over the integers at least. So I'm going to use the quadratic formula. I could do complete the square, but nobody likes to do that. So we'll use quadratic formula because this is non-factorable over the rationals, right? It's prime over q. So we're going to use quadratic formula. So we throw minus b plus or minus square root of b squared minus 4ac over 2a. So this is going to be 4 plus 4, right? So this is going to be 2 plus or minus square root 8 over 2, okay? And square root 8 is really 2 root 2. So there's a 2, a 2, and a 2. That all gets to cancel. And we have 1 plus or minus root 2. So we didn't get complex values. We didn't get any rationals, which we knew, okay? Because there was no fractions that we can use here, no integers, nothing, right? So here we have, again, a complex, or I'm sorry, an irrational pair, right? So I have my rational and its conjugate, right? 1 plus square root 2 and its radical conjugate 1 minus root 2. And so if we look at our values here, we happen to have all integers, but again, that goes with the radical zeros theorem. As long as they're all rational. 1 is rational, 4 is rational, negative 4 is rational, negative 1 is rational. They're all rational. So even though they're not fractions per se, right? It's not written as like 1/4. They are fractions. This is 4 over 1, right? 1 over 1. 1 over 1. So it works out that if they're all whole numbers, we can find a 0. So if we write this in factored form, it's x plus 1 squared, right? And this factors to x minus the negative root, right? 1 minus, and then its conjugate, which is 1 plus. You can keep it like this. It's very clear to see in this form what the 0 is. But maybe you want to distribute the negative sign in each, and that's fine as well. So, right, so here you get negative 1 plus root 2 and negative 1 minus root 2. It doesn't matter if you keep it in factored form, so you know, oh, this is the 0 and this is the 0, or you can distribute the 1. Both are fine. So let's do another example. Okay. So again, this is pretty straightforward. We used our standard method to whittle our polynomial down, then use the quadratic formula to find the radical zeros. Very possible that these could have ended up being complex. Most likely that's probably what's going to end up here, right? We're going to do the same thing. We're going to whittle our polynomial down till we can get to a quadratic. It'll either be complex or radical zeros at that point. So again, notice I don't have any irrational coefficients. I don't have any complex coefficients. So no matter what I do here, if I find one radical zero or one complex zero, its complex conjugate or radical conjugate will also be a 0. So let's go ahead and take this one. We have x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13. So the possible zeros from here are just 1 and 13. Possible zeros from here are 1 and 1. So really we just have plus or minus 13, plus or minus 1 as our possible rational zeros. So again, we always start with the easy one, x equals 1, and we will put our polynomial into the correct form, right? So we got the 1 minus x, 22 minus 30, 13. We start with 0, we'll get 1, multiply, add, multiply, add, multiply, add, so we get negative 13, multiply, and that's nice, it gives us 0, okay? So we'll do it again because this works once. So same thing, we'll get 1, and then 1, negative 4, negative 4, what's that, 13, positive 13, and it works again, another 0. Try it, let's see. Well, we got down to quadratic, okay? We can keep going, which I was very prepared to do, or we can just write this down and say, oh, well, look, x squared minus 4x plus 13. There's no factors of 13 to add to 4 or negative 4, right? 1 and 13 don't get there. So it's prime over the rationals. So even though I was prepared to continue going, I have my two zeros. I'm down to a quadratic. We'll just go ahead and throw it into the quadratic formula, right? So negative b plus or minus b squared minus 4ac over 2a. So you're going to get 16 minus some very large number. Okay, basically 4 times 13 is 26 plus 26, right? So what's that, 52? 16 minus 52, we're definitely getting a negative value. So we can simplify that down to plus or minus 3i, okay? You can do the little side work as you need to verify. So we have, again, the positive and the conjugate of it, right? So we have both pairs here. And again, we knew that was going to happen because all of our coefficients were real values, right? They're all rational. There is nothing crazy going on, no complex values, nothing for us to worry about. So if a radical showed up, we know its conjugate would be there. If a complex shows up, we know its conjugate is there, right? So if we write this into our factored form, this was a factor twice, right? X equals 1 was a repeated root. And then our complex values look like this, right? X minus one of the zeros, X minus the other 0. Again, you can keep it this way or you can distribute this negative. It's really up to you, okay? And so that's our factored form of our fourth degree polynomial that we had before, okay? So we're able to factor completely now, as long as there's only one quadratic or an easy way to separate two quadratics if they're both prime, right? So for the next example, okay, we want to find a 6th degree polynomial that is in standard form. Okay, so a lot of times I ask questions like this and then everyone just gives me the factored form. I can do that. That's easy peasy lemon squeezy. I want the real polynomial, right? Standard form, right? So as an actual polynomial like this, right? So a real polynomial as a polynomial, right? And the restrictions are that it has to have rational coefficients. So again, what that means then is that any zeros that pop up, complex or radical, their conjugates have to be there as well, right? So let's say that this is 1, 0, right? A radical. I have another 0 here that is a complex and a radical at that, right? And I have another 0 that's a whole number that has multiplicity of 2. So right now, I am gonna stop for a second, right? So you should take the time to pause this and try to find your answer on your own and see if you can match my answer that we're gonna go through together, right? This is 100% similar to a question I will put on exam. I put one of these on every exam that I have for pre-calculus, okay? So take a couple seconds to attempt that yourself. And we're back. So hopefully you tried your best and you worked through this and you got some kind of an answer. Hopefully it was right. Maybe not. It's okay if it isn't, right? So what we're going to do is we need to write these in their factored forms, right? First and foremost, okay? It needs to be a 6th-degree polynomial, right, with rational zeros. And I give you 1, 2, 3, and 4 zeros, right? So this rational coefficients is a big hint because that means that this should have its conjugate and this should have its conjugate. So that's the 2 missing zeros, right? 1, 2, 3, 4, and then these are the 5 and 6, okay? So we write these in their factored form, x minus 2 squared because it shows up twice, x minus 1/2 minus 3/2 root 2 plus its radical conjugate, then the complex 0 and its complex conjugate. Now, there's not any other way around this. We really just have to multiply everything out, okay? So you can pick whichever order you want to go. Obviously, this is probably the easiest one to first multiply out, and then probably this is the next one to multiply out, and then this is the next one to multiply out, and then you just keep working your way down until you have your polynomial. So that's really what we're going to do, is we're just going to keep multiplying stuff out, okay? X minus 2 squared is x squared minus 4x plus 4, okay? This is a little bit different. It is not a difference of squares, so you can't just say, oh, it's x squared minus and then this thing squared. It doesn't really work like that. You have to actually multiply it out. So we're going to have x times x squared, okay, minus x times 1/2, okay? So I actually do this a lot faster than that. So let's walk through this, okay? So all the things that are going to be multiplied times x, so I'm going to have x times minus 1/2, and then this will also give me an x times minus 1/2. So 2 of those is just -1, right? Negative 1/2 minus a negative 1/2 is 1. So that's why I have a minus x here. X will multiply times this 3/2 root 2. X will multiply times this 3/2 root 2 as well, okay? So we're going to have 1/4 minus 1/9 times 2 for the squared term, okay? So to clarify these, notice what happens when I have my x times this positive 3/2 root 2. It's actually a minus 3/2 root 2. This x times this one is minus and minus, so that's a plus. So I have x times one of them being subtracted and x times the exact same value but being added, so they cancel. So I don't have any 3/2 root 2 times x terms in the middle, right? So that means that the last value is this times this, right? This 1/2 minus 3/2 root 2 times 1/2 plus 3/2 root 2, okay? And I should be subtracting that, right? Well, a negative times a negative, so that's still a plus, that's fine. But on the inside, it's a difference of squares. So I square the first term, which is 1/2. 1/2 squared is 1/4. And then I squared the last term, and I subtract them because it's a difference. And so that gives me 9/4 times root 2 times 2 is 2. So then those will cancel, and I can add these together, right? So they already have a common denominator, so I won't cancel them when I add them together. On the next line, you'll see that this will be 1 minus 18/4, right? So I can write this as negative 17/4. It'll be easier to write that than it will to cancel this and then then try to subtract. Okay, so this is going to work the same way. The x times the x will give me an x squared. Okay, when I go x times this, I will have a negative 1, right? When I go x times this one, I will have another negative 1. So that will give me a negative 2x. Okay. When I go x times this value, this I root 2, it's actually positive, right? Because this negative and negative gives me a positive. So this is actually I root 2x. And then when this x goes against this root 2, it's the same thing, but the opposite sign, because this distributes to a negative. So there is no I root 2x terms going on. Okay. So the next thing I have then is this minus and a minus, right? These two last terms, negative times this thing, minus times this thing will give me a plus. And inside of the next parentheses, I just have a difference of squares because I'm multiplying 1 plus I root 2 times 1 minus I root 2. So I square the first term, which is 1. Okay. I have a difference, so I put a minus, and I square this, so that'll give me 2i squared. And that's my polynomial. Okay. Now again, maybe that was confusing to you, and that's fine if it was. That's why I asked you to go through this first. If you want to be extremely clear on what you're doing, you can distribute your negative sign across your signs, and you can do your double distribution, right? And you'll make sure that you're getting the right values. I've done this so many times in my life that that's how my brain works. So I'm really just walking you through the method that I do so you can try to expand your ideas of how this works. Okay, so again, stick to what you're comfortable with. Don't try new fancy things if it's not going to be super comfortable for you, but that's the way that I'm looking at this. I'm multiplying it in the FOIL order, but I'm taking consideration the signs as I do so, and what's canceling and what's not, basically. Okay, so here I don't have anything to simplify. Here I do. It'll be x squared minus x. This can combine, as I said before, to negative 17 over 4. Okay. This will be x squared minus 2x. So this will turn into, remember I squared is really a negative, so this will turn into 1 plus 2. So this will be x squared minus 2x plus 3. Okay. So now that's a lot nicer, right? I still got to multiply all this stuff out. It's still a lot of work. The one with the fraction is probably going to give me the most problems. Okay. So what I'm going to do is I'm going to multiply the x squared minus 4x plus 4 times the x squared minus 2x plus 3. And I'll leave this middle one for last. Okay, I'm pretty sure that's what I did, because again, I would rather introduce fractions in the very last step instead of somewhere in the middle or somewhere in the beginning, and then have to do all this crazy work with fractions everywhere, right? So I'm going to take x squared and multiply it times the whole polynomial. I'm going to take minus 4x and multiply it times this whole polynomial. I'm going to take 4 and multiply it times this whole polynomial. So this is still here, okay? This is x to the 4th. There is no other x to the 4th terms, okay? So minus 2x cubed plus 3x. Here I distribute the 4, so minus 4x squared plus 8x, minus 4x cubed plus 4x squared minus 12x, okay? And here I just multiply everything by 4, so 4x squared minus 8x plus 12, right? Very similar to before, but without the extra x and without the sign change. So now I look for all of my like terms. X4 stays. Okay. The cubes are here. So that's minus 6x. Oh, I just have them wrong. Right. So that's minus 6x. The squares are 3 plus 8 is 11. Plus another 4 is my 15. Okay. And then for x's, I got minus 12 and minus 8. So that's minus 20. And then this is the only constant term. Right. So now I do the same thing. I'm going to distribute this across this polynomial. So x squared times this whole thing, okay, minus x times this whole thing, and minus 17 over 4 times this whole thing as well. All right, and I'm just going to distribute, right? X to the 6th minus 6x to the 5th plus 15x to the 4th minus 20x cubed plus 12x squared. So forth and so forth and so forth. So we'll write all this out. There's a lot, as you can see, it takes up 2 lines. So in the next step, it's very possible that I write it all out and have already combined it. So let's see. Okay, I did 6x to the 6th, right? Because that's the highest degree. and then I'm going to combine all of my constants, right? So just so that we're clear, the only constants I have is 17 over 4 times 12, okay, because everything else will be multiplied times either x squared or x. So just so that we're clear on the first term is x to the 6th, okay, because there's no more powers that will give me a 6th degree. The last term is 17 times 3, right? 12 over 4 is 3. 3 times 17. Okay. So we have, oh, I guess I did do it one at a time. I'm sorry. So this is the first one, right? The first 4 where I'm multiplying that x squared in. The next one where I'm multiplying negative x in. And the next one where I'm multiplying negative 17 over 4 in, right? So that gives me a 51. So now I combine all my like terms. X6 stays. Negative 6, 5 minus an x to the 5th is minus 7. I got 15 for a 4 here. I got a 6, so that's 21. And then this crazy value here for a 4th term also, 4th degree, so that's 67 over 4. Same thing, I'm going for the cubes, right? Minus 20 minus 15 is minus 35, plus this 51 halves, so I get 19 over 2 negative. X squares comes to this, and for my x's, I just have 12 and 85, right? So 85 minus 12 is 73. This is the only constant, right? Therefore, the polynomial that works for me is this one. So notice that all of my coefficients, there's no radicals, there's no complex, but there are fractions, right? They're all rational. So they're whole numbers or fractions. And that's the way it works, okay? So yes, it is a lot of work, but that's how you build a polynomial out of your given information. Thanks guys, see you on the next video.